Good morning to you all. Welcome to this video. Today we are going to solve the May-June uh, 2024 variant 61 in paper in curriculum 972. It will also be very useful if you get a copy of this page and download it and you follow with it while we are solving the exam. This is always going to be very useful. So we're starting with the first question. It is telling us a student investigates the stretching of a spring, okay, and he's showing figure 1 where we are having a spring, as you can see it. This is a spring, okay. We have a meter ruler. He's kindly have labeled them on the figure, okay. This is the clamp, so this is the setup. Uh, the students The student measures and records in table 1. So we are going to have a table 1. The unstretched length L knot of the spring. It doesn't include the loops at the end of the spring in the measurement. The value L naught is the length of the spring when the load is 0. So those are three main points that you have to just keep in the back of your mind. So what he is telling us that the unstretched string or always the measurement is going to be for the part of the string not including the loops. Okay, so this is the length of the spring. Okay, describe so this is the first question actually. Describe one technique you would use to obtain an accurate value for L naught. Draw a diagram to illustrate your answer. So to go through this, so always remember, as we have previously mentioned, the way always to take a measurement in this kind or in this setup, always to have a meter ruler which is close enough to the spring. It need to be parallel to it, exactly parallel to it, and then you can use a set square to help you take an exact reading, and always set up your eye to be perpendicular to the reading so that you can avoid parallax error. So those are the things that we need to mention. So if he is asking us to make uh, a drawing, this is what we are going to do. This is a stand, okay. uh, we have the clamp over here. Here is the here is the spring, okay. And now we have a meter ruler which is parallel to it, okay. This is how we are going to draw the meter ruler, okay. We are going to do some lines over here, okay. We are going to use a set square, so this is how we are going to uh, point the set square, okay. And here is our eye perpendicular to the meter ruler to take the measurement, okay. Then we can now answer in writing, okay. 1 point, the first point that we can write: keep the meter rule as close as possible to the spring. make sure that they are perfectly parallel to each other. Another point that you can also measure or include in your answer, use a set square to help take an accurate reading on the meter rule. Okay, another one you can also mention, make sure your eye is perpendicular to the reading to avoid parallax error. Okay, any of those two is going to be enough to answer, but if you give three, this is going to be perfectly better. Okay, let us go to question B. The student suspends the load L is equal to 1 Newton, okay, from the spring. He records a new length L, now the length is L, in table 1. He calculates the extension E of the spring using the equation. So he already gave you the equation that you need to use, okay, and records the value of E in table 1.1. The student repeats the procedure using loads 2, 3, 4, and 5. So these are the values we are going to see in the table. The recording and results are recorded in table 1.1. Okay, good. Calculate the extension E of the spring using the equation. Okay, again, he reiterates the equations that we need to use when L is equal to 5 newtons. Okay, record this value in table 1.1. So this is the table that we are going to use. First thing that you need to check in any table that you are given, always make sure that you have the column labels, column units are there and complete. Okay, sometimes he doesn't give the units and you need to write them. Okay, if that was the case, he's most probably are going to see it in the questions. Okay, just one thing to note about the length of the spring while it is not stretched. We know that the length when it is not stretched, it is when the load is 0. So this is the load, this is the length of the string L naught. So we can take a note, L naught is equal to 2.1 centimeter. Okay, this is how we came to know about L0. Okay, now he's asking us to complete the table. He asks us to get the extension when the load is 5 Newton. So we know this is going to be what? L minus L naught. Okay, we know L 23.7. We know about L, which is 2.1 centimeter. So do the math and you get 21.6 centimeters. Okay, very simple. So now he is asking us to make a graph plot for the readings, and most of the time they are telling us which axis is which. So he's telling us that for the y-axis we have to put the load, for the x-axis we have to put the extension. The other important instruction he is giving us that we should start from 0, 0. So these are the instructions that we are given. Okay, to make things clear for you, let me okay, good. Now let us make the label. Okay, so if we are going for the x-axis, let us start labeling the x-axis. Okay, how many squares we are going to have? We are having to get sorry, 1, 2, 3, 4, 5, and 6 squares. Okay, if we are having a look at the table, it's we are going to put E on this axis, extension in centimeters. Okay, we are going to put the load L in Newton in this axis. How many squares do we have? 1, 2, 3, 4, 5, and let us say 6. Okay, having a look at the values in the column with the extension, we see goes from 0 to 21.6. So a good scale that I think might be a good one might be each square is 5 centimeters. So let us see. If I say 5, 10, 15, 20, 25 centimeter. So most probably the drawing is going to be end in will take around 1, 2, 3, around 4 or 5 squares, relatively 5 squares on the x-axis. So what about the y-axis? Okay, it goes also from 0 to 5. So we have 0, we can have 1, 2, 3, 4, 5. Okay, I think this is going to be a good scale. Now let us start making our points. The first point, as you can see in the table, is 0 and 0. Okay, so it is this one, and the plot means that the straight line or the plot is going to pass through the origin. Let us go to the second point. L is 1 Newton and E is 3.9. Okay, how am I going to see mark 3.9 on the x axis? This is how we are going to do. So each small scale, okay, one small scale on the x axis is 5 divided 10 is equal 0.5 centimeter. Okay, so each small scale is 0.5 centimeter. So let us start counting. Okay, each 1.5, this is 1, 1.5, 2, 2.5, 3, 3.5, and here is 4. So it is a little bit short of 8 small squares. A little bit short of 8 small squares. Okay, when we are going to mark it, okay, where we are going to mark it, it is going to be here. How do we mark it? Remember, this is what we have said. We can use a point with a small circuit around it, or equally well, we can use a small cross. Okay, most of the time I do a point with a circle around it. Remember that something like this is not acceptable as a point. Something like this is also not acceptable. What is acceptable is, okay, a small point like this, okay, with a small circle around it. Okay, so we are done with 2 points now. Okay, we go to 2 and 8.5. So this is on the y-axis, this is a 2. Okay, now we are going for the 8.5. Okay, half 7.5, 8. This is 8.5. Okay, another small one. We go to 3 and extension is 12.8. So 5 small squares gives us 12.5. 6 small squares give us 13. So it is in between 5 small squares and 6. So let us count 1, 2, 3, 4, 5, and 6. So it is somewhere over here, almost here. Okay. Now we go for the 4 and 17.2. So it is easy. 4, 17 point. So 5 small squares are 17.5. 4 small squares is 17. So it is mid between 4 and 5 squares on the x-axis. So it is somewhere over here. Okay. And we got 5 and 21.6. So this is 5. Okay. And 21.6. Okay. This is 20. 20.5. 2 squares is 21. 3 squares is 21.6. So it is, sorry, 21.5. 22. So it is around here. Okay. Now we are going to make the line. Okay. What we are sure about this line is that it starts from the origin. So set your meter rule to go through the 0 point. Okay. Move around your meter ruler. Sorry. Move around the meter ruler so that you get as many lines as possible to go through the line. Okay, so we try to judge which is the best line. Okay, can you see this is not a very good line? Too many points are sitting away from the line. I think this is a good one, not a very good one. Okay, maybe this one is a good line. Okay, let us take this as the line that we are going to draw. Okay, here it is. Always remember to do the graph plot with a pencil. Okay, now let us go to next step. Determine the gradient G of the graph. Show all your working and indicate on the graph the values you use. Okay, now as you remember how to get the gradient, we have to draw a right angle triangle. Okay, uh, not a small one, not a huge one, but a reasonable one which covers more than half the lines that you have used. Okay, so let us do the graph plot. Okay, let me take something from here. I will take it from here. I will drop the straight line straight down here. Okay, so this is the line I'm using. Okay, I hope it is clear for you. You can see it. Okay, now we are going to go to this line. I'm going to use this one. You got the choice to use different lines for sure. Okay, okay, so let me take the points. Okay, this for the for this line, well, I am just marking it for you to see. Okay, you don't have to do it this in the exam, or actually you shouldn't do this in your exam. Okay, I'm just marking it for you to see it. Okay, this one. Okay, the reading here is 1.5. Okay, the reading here above is 5.5. Sorry, 5.1, 5.1, 5.2, and we have kind of 5.3. 1.1.2. Okay, 5.3. 5.3. Okay, now we take the reading down here. The reading down here is 20, 21, 22, 22.5, 23. Okay, this 23. Okay, so this reading is 23. Okay, we take the reading down here. Okay, it is 5, 6, and it is 6 over here. Okay, 6. Okay, do we have all the information needed to calculate the gradient? Actually, yes. Okay, for the y, we have 5.3 minus 1.5. We have divide 6 minus, or sorry, 23 minus 6. Okay, let us do it on the calculator. Okay, 5.3 divide, sorry, minus 1.5, we get 3.8, divide, and we got 23 minus 6, which is 17, equal 3.8 divide 16 equal 0.2375. So we get here the gradient is 0.2375. We can write it to three significant figures. It is 0.238. Remember the units we have on the y-axis is newtons. On the x-axis we have centimeters. So the units is Newton per centimeter. Newton per centimeter. Recall G is numerically equal to the spring constant. Record the value of G to a suitable number of significant figure for the experiment includes the unit. So it is actually just G is equal to K, which is 0.238 Newton per centimeter. Okay, I think we are done with question number 1. Okay, let us go to question number 2. A student investigates the resistance of a wire. Okay, here we have a wire. We have the circuit, we have a power supply. This is the power supply. We have a switch, we have an ammeter. This is the wire we are investigating, and here we have a voltmeter. Okay, the student measures the current I in the circuit. She places the sliding contact at the point S at a distance D is equal to 50 centimeter from B. Okay. She measures the potential difference V50, okay, across the length D of the resistance wire. Okay, so he measured this one. And now he's showing the reading on the ammeter and voltmeter scales. And he is asking us to take the reading from the scale. So the first thing to always do over here, okay, you need to see what is the smallest count this scale can read. Okay, to do that, okay, we have for the ammeter, this one, we have from 0 to 0.2, we have 10 division, we have 10 small divisions, so we divide by 10. Okay, so each small division is 0.02 amps. Okay, we do the same for the voltmeter. Okay, we need to see what is the smallest scale that can be read, or values that can be read with this scale. So it is from 0 to 1. Okay, it is 1. How many divisions? We have 5 small divisions, so each one is 0.2 volts. We know now everything that can help us take the reading. Okay, now let us take the reading for this one. So this is 0.2. Okay, till the center here is 0.3 amps. Okay, 0.3 amps, 0.32, 0.34, and the pointer is standing at 0.36 amps. Okay, so here we have 0.36, and we don't see a unit, so we have to put the units ourselves. Okay, now for this one, here is 1. Now this is 1.2, and the scale stands on 1.4 volts. Okay, we have 1.4 volts. Okay, these are the values that we can take from the scale that he's showing us. Okay, we go further. calculate the resistance R50, and he is telling us that to calculate it, we have to divide V50, which we had previously, divide by I. Okay, so it is going to be 1.4 volts divide 0.36 amps. Make the division with your calculator, and we get 3.89 ohms. Okay, now we write the value over here, 3.89. We don't see a unit, so we have to put the units ourselves. Calculate R1, a value for the resistance per centimeter of the resistance wire using the equation. Okay, R50 divide D, and he's giving us D as 50 centimeters, so we all have all the information. So 3.89 ohms divide 50 centimeter. We do the math, we get 0.078 ohms per centimeter. Okay, we can write it like this, or we can make a unit change to make it ohms per meter. So if we would like to do it ohm per meter, this is how to do it. So 0.078 ohms, we don't do anything by the ohm, divide the centimeter. To make it a meter, we have to multiply 1 by 100 or 10 to the power minus 2. Okay, this is 1 centimeter. So we multiply by 10 to the power minus 2. Okay, now we can see that the 10 to the power minus 2 is going to go up over here. Okay, so this is going to be 0.078 ohms by 100 divide meter. Okay, then it is going to be 7.8 ohm. 7.80 ohm per meter. Okay, sorry, we don't have a zero over here. Ohm per meter, or 0.078. So it is at your convenience what you would like to do with it. Okay, now the student repeats the procedure in Kaza using D is equal to 75 centimeter. Calculate R using the equation R يساوي this. So he found R 75 2.2, R 75 to be 6.1, and he found R2 is equal to 0.081. Okay, and the units, I guess the units here, he didn't ask us, but this is the volt, here is ohm, here is ohm per centimeter. Okay, state whether your result supports this suggestion and justify your statement by reference to the result. Okay, and this is how I always do it. So what he is asking now, if R1 is equal to R2. So he's asking us to tell him if we think that R1 is equal to R2. So how do we decide? Is it just by looking at the two values and looking at 0.78 and 0.081? If they are close enough, we just say that yes, they are equal or not. But this is not the way I always do it. The way I do it is I do calculate this value. Okay, so I calculate the difference between the two values. Okay, I divide by the smallest of both of them, and I then multiply by 100. So this is what I usually calculate to answer this question. I calculate the difference minus, okay, I divide by the smallest of them. I then multiply by 100. If the result of your calculation is less or equal to 10%, then we can say that both values are equal within experimental accuracy. If the result of this calculation is larger than 10%, then we can fairly say that they are not equal within the experimental accuracy. So let us do the calculation. Do the calculation with your calculator, and you get something like 4%. Okay, so we did the calculation. The answer is yes. They are equal. Okay, the justification, the relative difference between R1 and R2 was found to be approximately 4%. Hence, they are equal within experimental accuracy. Okay, and this is how I always answer this kind of questions. Okay. The student plans to plot a graph of resistance R against length D to test the suggest suitable additional values of length D. So it is very easy. We can typically suggest values in the range between 10 centimeter and 100 centimeter. Any value should work. Okay, so we can say that 10 centimeter, 20 centimeter. We have 50 and 75, then we don't use 40, 80 centimeters, 90 centimeters. Okay, so kind of this. Then he is telling us a variable resistor is a circuit component that can be made using a coil of resistance wire. Draw the electrical symbol for a variable resistor, and this is the symbol for a variable resistor. Or this one. You can use this one or that one. Both are okay. Now we go to question 3. A student investigates the image produced by a lens, okay, shown in the setup. Okay, he's showing us the setup. Here we have a lens, we have a light source, we have an object here, we have a screen. Everything is detailed. Okay, he's telling us that figure 3.2 shows the height h0 of the illuminated object, and he's telling us this is the length of the illuminated object. So the object is this square. Measure h0. He is asking us to do the measurement for h0. Okay, just bring on your meter ruler. Okay, and take a reading. Okay, so this is how we are going to do it. Okay, this is how I'm going to do it. And if I take a close look at the measurement, I can see that H naught is 1.6 centimeter. So I record here 1.6 centimeter. I don't see a unit, so I write it myself. Then he's telling us that figure 3.1 is drawn to a scale, meaning that it is not the exact sizes as the experiment. It is drawn to a scale. The actual distance u between the illuminated object and the lens is 20 centimeters. So in his experiment, he set u to be 2 centimeter. Measure the distance x. So he's asking us to measure this distance x. Again, we get a meter ruler. Okay. We carefully set it like this. Okay, as you can see, I can read a distance of 2 centimeters. Okay, so it is 2. It is 2. So x is 2 centimeters. X is 2 centimeters. Okay, calculate the scale ratio R using the equation. So he's giving us the equation to calculate the scale ratio. The value of u he's giving us here as 20 centimeter. X is 2 centimeter. Then R is 10. Does it have units? No, it doesn't have any units. Okay, so it is 10. The students move the screen until a focused image is formed on the screen. On figure 3.1, measure the distance. Again, we use our meter ruler and measure this distance y. I did the measurement and I got 6.2 centimeter. Okay, so y is 6.2 centimeters. Okay, he got the units. Now he is telling us to give him the right or the actual value for the image or the value of v, and he's telling us how to calculate it. He's so kind and generous. It is r times y. R is 10, we got it from previous step, and y is 6.2. Then this v is 62 centimeter. Okay, he got the units. Okay, I don't need to write it. Now calculate the focal length f of the lens using the equation. He is again very kind to tell us which equation we are going to use. So f is going to be u, which is 20 centimeter. Okay, u equal 20 centimeter. V is equal to 62 centimeters. Okay, so 20 times 62 divide 20 plus 62. We do the math and we get 15.1 centimeter. Okay, 15.1 centimeter. In this type of experiment, it can be difficult to judge the screen position that produces the clearest image. Okay. Suggest 2 precautions or techniques to overcome this difficulty. The first thing that you can always make sure to carry this type of the type of investigations is always to carry it in a dark room. Okay, so we are going to tell him carry out the experiment in a dark room. It helps a lot to get a clear image of the object. Okay, the second precaution, or what we can usually do, move the screen forth or back and forth till a clear image is found from both directions. Then use the average. So let me tell you, just explain a little bit more about this one. Okay, what do we mean by this? So you have this setup. Okay, you have your object here. Okay, we have the lens over here. Okay, and we have the screen over here. Okay, and this is our meter O. So what we are going to do, start, okay, with the screen on this side. Okay, then start moving slowly in this direction. Okay, till you get a clear image. Okay, till you see a clear image. Say we see it over here. Take a reading. Call it x1 or whatsoever. Okay, now do the same, but sorry, do the same, but this time start with the screen over here, move it into this direction, move screen to this direction till you get a clear image. Clear image. And call this x2. So we got a clear image when we were moving the screen in this direction, and we got another clear image when we were moving the screen in that direction. We call the first one x1, the first x2. Then we calculate the average. x1 plus x2 divide 2. Okay, usually they are almost one or few millimeters away. Okay, so this is one way of improving it. So we get x. Now this is the value you are going to use in further calculation. So this is what I mean when I wrote this statement. Move the screen back and forth till a clear image is found from both directions. Then use the average. Okay, I hope this is clear. You don't need to write this. You don't need to write this or explain it in the exam, but this kind of a statement should be enough for the examiner to understand what you mean. A student, this is the last question, which is about how you plan an experiment. A student investigates the bending of composite strips of wood when they are located at one end. Okay, the composite strips are made from identical layers of wood stuck together as shown in figure 4.1. So this is the bunch of woods or the strip of woods that we need to investigate. And this is the experimental setup that we are going to use. And what we would like to investigate is the bending of the composite strips. Okay, as they are loaded at one end. So kind of he told us which are the dependent and independent variable. Plan an experiment to investigate how much composite strips bend when they are loaded at one end. Shows the setup the student uses. The student has a number of composite strips made with 2 or more layers of wood. Okay. State the variables that you are testing, list any additional apparatus that you would use, explain briefly how you to do the investigation, state. Okay, let us go one by one. State the variable that you are going to test. Actually here, one of the variables that is he asked explicitly to investigate is the bending. Bending. Okay. So how we are going to measure the plan experiment shows the setup the student use. The student has okay. So how we are going to measure the bending? Okay, we have just need to be a little bit creative. So what does bending means here? Okay, so if we load a weight over here at the end of this composite strip, what we expect to happen that this one is going to bend like this, right? The strip is going to bend. So this is what we expect to see, a bending strip like this, like this. Okay, how I'm going to do the measurement? Okay, I'm going to use a meter rule. Sorry. I'm going to use a meter rule over here. Okay, to help take the reading for the bending. Okay, this is the distance or the bending. Let us call it L. Okay. So the bending is going to be the dependent variable. Now, which variable is going to be independent? Actually, you have a number of choices. Either we vary the load, the weight, each time we use a different weight. Okay. So it's going to be additional weights. Two, we can use a variable as number of strips. This one, the number of layers, in a strip. Sorry, number of layers in a strip, or distance at which the weight is hanged. Means that we can change the distance the weights are hang each time, and we measure this distance as independent variable. Okay. My personal favorite will be to use different weights. Okay, this one. So for my choice, I will use bending with a variable L or symbol L, and weight with simple W. Okay. Now let us write the answer. So we have decided what we are going to do. Okay. So we will investigate how far the beam bends under the effect of different weights. Now we have defined the dependent and independent variables. Hence, we use the bending L as dependent variable and the weight W as independent variables. Okay. Now, which variables are we going to keep constant? We keep the same beam over the whole experiment. What else we should keep constant? We also keep the position where we hang the weight constant. Okay. The bending is measured with the help of a meter rule fixed as shown in the figure. Different loads are used and the corresponding bending is measured and tabulated in the table below. Okay, here is our table. So we're going to present our values. We have W, weight, it is measured in Newton. We have the deflection, we called it L, it is measured in centimeters. How we are going to report our result? We make a graph plot of W on the x-axis and L on the y-axis. Okay. So this is one way of answering it. Maybe you are interested, instead of varying the weight, you can tell, okay, this is another answer. Another answer. Okay. We keep the weight the same, but vary the hanging the point of hanging the weight. Okay, then we are going to have a table and now we have a table which is, let us call it H centimeter, okay, L centimeter, and this is how you do it. This is the clamp. Okay, so this is the distance where we hang the weight. Okay, this from here to here, H. So each time we change H and read the bending. So this is another way of answering this question. Okay, another way. And think we are done with your exam. The time is very tight, so you need to practice a lot. You might not have enough time to go and check your results, so always make sure that you get it right from the first time. Good luck and see you in another video. Thank you.